Welcome to Maths with EJD. In this video, I'll be talking about complex numbers and hyperbolic functions. What is the connection between them? Or like some people would say, what's the nexus between complex numbers and hyperbolic functions? So let's go. Let's start with the connection between hyperbolic functions and complex numbers. So hyperbolic functions such as sine x and cos x have a strong connection with complex numbers due to their relationship with complex numbers, due to their relationship rather with exponential functions. So for instance, you can interestingly, I have a whole playlist on complex numbers where we saw actually how we can represent complex numbers in both polar and exponential form. Okay. And of course, you see, basically hyperbolic functions are exponential in nature. So because of that exponential expression between the two, we can actually find some relationships binding them together. So for a complex number, for instance, for a complex number, because the general form of a complex number is z equals x plus iy. So for this kind of complex number, where I is the imaginary unit, and if you're new to that, I is basically the square root of -1, and that's what makes a number complex. So where I is the imaginary unit, so we see the hyperbolic functions can be represented using Euler's formula. Okay. So, and let's go. First of all, let's look at hyperbolic sine, which is sine, and cosine. That means hyperbolic cosine, which is cos. So if you look at that now, so we see that sine z is equal to e raised power z minus e raised power minus z divided by 2, while cos z is equal to e raised power z plus e raised power minus z over 2. In fact, I'm still building the playlist on complex numbers, but I know I've talked about complex functions, and these are very good examples of complex functions. So in this case now, so if we now have, say, for a complex number, z, which is equal to I raised power x. You see, it can have a place in all these things. So for a complex number, z equals I raised power x, right? Where x is real, where x is real, because we already know I is the imaginary unit, square root of -1. So where x is real, then we can say that sine z can become something like sine ix. So anywhere you see z, you put ix. And that is simply e raised power ix minus e raised power minus ix all over 2. So if you remember in the last video, if you have seen the last video, where we are comparing trigonometric and hyperbolic functions, you see that this is exactly the expression for, so this expression is the same thing for I sine x. Okay. So because you know that sine x is actually equal to e raised power ix minus e raised power minus ix divided by 2i. So this I now is what comes under here. When you, okay, let me just even express that, So basically, right, we're saying that that is why sine x is the same thing as e raised power ix minus e raised power minus ix divided by 2i, because this I is here. So you can see that sine ix is the same thing as I sine x. Very interesting connection right there. So of course, so we can try something for cosh too. If you put ix for z for cosh, but then I'm not going there. So we see that this simply shows, that hyperbolic functions for purely imaginary arguments actually relate directly to trigonometric functions. So we are seeing a kind of establishment again between hyperbolic and trigonometric functions. So they relate directly to trigonometric functions. Okay. Now, having talked about the connections, right? Okay. Okay. I think I should also do this. So for cosh, sorry. For cosh now. So so if you have cosh, okay, let me use another color since, so for cosh z will be cosh ix. That's if z is ix now, and that is equal to e raised power ix plus e raised power minus ix divided by 2. And of course, this is exactly the expression for cos x. So that shows us that cos ix is the same thing as cos x. So, and this, of course, this shows that hyperbolic functions for purely imaginary arguments relate directly to trigonometric functions. So in summary, right, we have that sine ix is equal to I sine x, while cos ix is exactly the same thing as cos x, like that. So this is really cool, really important. So now it's bringing together complex number, hyperbolic function and trigonometric function at the same time. Really beautiful connection right there. Okay. So this shows that hyperbolic functions for purely imaginary arguments relate directly to trigonometric functions. Now, let's go ahead to talk about hyperbolic identities. Hyperbolic identities. So hyperbolic identities involving complex variables. So hyperbolic identities including involving complex variables. Several identities involving hyperbolic functions can be derived using their exponential definitions. Okay, several of them. Okay, let me just write that. Okay. Several identities involving hyperbolic functions can be derived using their exponential definitions. So for instance, if we talk about addition formulas, say we have sine z plus 1, I mean z1 plus z2. Of course, we already know that is sine z1 cos z2 plus cos z1 sine z2. That goes. And then, of course, we know that cos z1 plus z2 equals cos z1 cos z2 plus sine z1 sine z2, like that. So that's the addition formula. Then if we, so talking about hyperbolic identities involving complex variables, right? So now, having stated that, let's look at Euler's formulas for hyperbolic functions. Euler's formulas for hyperbolic functions. Okay, so here, e raised to power z is equal to cos z plus sine z. Okay, I mean, you can practically try this out. Okay, I mean, just look at this. This is e raised to power x plus e raised to power minus x divided by 2. So this is actually divided by 2. This is divided by 2. Then plus, so this is cos z. Sin z is e raised to power x minus e raised to power minus x divided by 2. Everything divided by 2. So you can split it up like this. So you see that this cancels this. Okay. What's canceling now? Okay, this cancels this for sure. And then you have and then you have e raised to power x over 2. In short, e raised by x over 2, that's half e raised by x plus another, so this now plus this plus another half e raised by x, and the answer is simply e raised by x. That's why e raised by x is actually cos z plus sine z. So this is just by the way. And then on the other hand, you have e raised by minus z. E raised by minus z is simply the same as cos z minus sine z. So this is another one like that. Of course, you can do exactly what I did. So you get e raised by minus z. So we have the Euler's formulas for hyperbolic functions that way. And then we can move on to the third one. We can move on to the third one, which is about relationships. So relationship to trigonometric functions. Of course, we saw one already. We saw that the hyperbolic function that take purely complex arguments actually relate directly to trigonometric functions, since we saw that sine ix is the same thing as I sine x, and cos ix is the same thing as cos x. So talking about this relationship now, so we say that for a complex number, z, which is equal to x plus iy, the hyperbolic function, the hyperbolic cosine rather, the hyperbolic cosine and sine can be expressed as cos x plus iy, cos x plus iy, of course, that is cos x cos x plus iy can be expressed as cos x cos. Okay, well, let me just do it the way it should be, then we'll simplify it. So this is cos x cos iy normally, right? Plus that sin x sin x sin iy. Okay, that is what that is like. But then we already know that cos x, of course, cos x is cos x, but we know that cos iy is simply cos y without the I, right? So cos iy is cos y. Then sin x, of course, remains sin x is sin x, right? But sin iy, we know that sin iy is actually I sin y from what we saw previously. So in this case, now we can tidy this up to have cos x cos y plus the I comes in front now, and that is sin x sin y. Okay, so that goes. And then, of course, we can try the same for sin x plus y. So for sin x plus iy, that is, we have, again, sin x, sin x rather, cos iy, okay, plus x cos x sin iy. Again, using the same logic, this is sin x normal. Cos iy is simply cos y, like we know, plus cos x, of course, that's okay. Sin iy again is I sin y. So if you put all that together, we get sin x cos y plus I cos x sin y. So that's coming from the simple fact that sin ix is simply I sin x, and then sin rather, and then cos ix is directly cos x. So that's what has led to these two now. Okay, so we see that we see sine, cos, and complex numbers coming together. So let's talk about applications in conformal mapping, in complex analysis rather. So application of hyperbolic functions in complex analysis. So let's do that. Okay, so we go right now. So applications in complex analysis. Okay, so one, we can talk about conformal mapping. One is conformal mapping. Okay, so hyperbolic functions are used in conformal mappings where they help transform, complex functions in ways that preserve angles. For example, the mapping W equals sine W equals sine Z transforms the strip minus pi over 2 less than, so some special kind of Z. Let me just write this way. So less than f of Z less than pi over 2 in the complex plane, in the complex plane to the entire, in the complex plane to the entire complex plane, excluding the imaginary axis, the imaginary axis. So that's one application in conformal mapping right there. Okay, so let's talk about two, solving complex differential equations. Solving complex differential equations. Okay, so we see that hyperbolic functions often appear in solutions to complex differential equations. Okay. For instance, the equation, we've seen this a couple of times before now, like probably in a previous video. So for instance, the equation y prime prime minus y equals 0 has solutions involving hyperbolic, sine, and cosine functions. Which can also be extended to complex variables. So you remember that if you differentiate sine x, you get cos x. Okay, well, let's stay with hyperbolic function. If you differentiate sine x, you get cos x. If you differentiate cos x, you get sine x back. And that way you can actually have that d squared sine x dx squared is the same thing as sine x. That means you have d squared y equals y. And that's why d squared y dx squared minus y is equal to 0. So that's the kind of thing that comes. Of course, the same applies to cosh. Differentiate cosh, you get sine. Differentiate sine, you get cosh back. So that's why the solution of this would involve both sine and cosh together. Okay. So we move on to the third possible application of hyperbolic functions in complex analysis. So we have what we call the analytic continuation. Analytic continuation. So we can see this in terms of, I mean, as analogous to continuity or so in real numbers, which I talked a bit about. I think I have a video on limits and continuity, right, on under basic calculus. So hyperbolic functions are used in analytic continuation, where a function defined on a subset of the complex plane is extended to a larger domain. So since hyperbolic functions can be expressed using exponential functions, they are inherently inherently analytic. They're inherently analytic and can be extended over the complex plane. So from that, we move to the final application we'll be considering for now, which is residue calculus and complex integration. Residue calculus and complex integration. Okay, so in complex analysis, hyperbolic functions appear in residue calculus and integration. For example, integrals involving hyperbolic functions such as the integral of 1 over cosh z dz. So integrals like this are actually solved using techniques from complex analysis. Leveraging the properties and identities of hyperbolic functions. So we've seen some of those identities already, so we can actually work around this. So by the time I extend my playlist on complex analysis, I know I'll get to this point, so I'll be talking about poles and residues and things like that. So at this point, we've come to the end of hyperbolic functions, except as somebody makes a request that I've not already covered. Maybe I can think of extending the playlist, but for now, I want to think I've come to the end of hyperbolic functions. Thank you for coming along in the journey. So if you have not subscribed, be sure to do that, and of course hit the notification bell so you can always get alerted each time a new video is released. And don't forget to comment, like, and share. Thank you so much for always being part of this journey. See you next time. Bye.